Okay, so today we're going to talk about the science of epidemics. So it's very relevant, um, right? Because that's what we're all going through and that's what we're experiencing. So since this is the science of everyday materials and everyday life, I thought that this is something that's particularly relevant, even though I hadn't planned on talking about this when the course started, right? Would you agree that it's relevant?
Yeah, it's pretty relevant.
Yeah, right. That's what everybody's talking about. Okay. So before that, I'm going to talk about a bunch of related phenomena and exponential growth as well as uh, you know so growth of a population is similar to growth of like a virus. So what do you see in this picture? Can you see the slides?
Yeah, isn't that like just a herd of, is it deer?
Yeah,
Or,
it could be deer. It looks a little bit different from deer, but that doesn't matter. It's just a herd of herbivorous animals, and they're sitting on grass, right? Why are they on the grass?
that's their food?
Yeah, that's their food, right? And there's a lot of deer.
Hmm.
So we'll talk about how the number of deer would be growing, right? And how they grow. But before that, so what is this? What do you think this course has been about? This is something that I wanted to ask you guys. Any thoughts?
How we can find science in everyday things,
Yeah.
like
So how you
objects.
can find science or learn science from everyday things, right? Um, and this has been another group said this is basically applying scientific concepts to understand the real world, also your world, your everyday world. So basically, the idea is through certain themes in everyday life, or such as materials, you can learn a lot of concepts like physics, chemistry, biology, and mathematics. Um, and phenomenon or things that you do, like for example, making coffee, you could learn coffee doesn't say that, oh, well, I'm chemistry, so you can't learn physics from me, right? It's an integrated process. And that's how most natural phenomena are. They're integrated with all the different sciences. Right? Um, so what else do you think?
How science plays a part in our environmental landscape
What's that again?
is showing us how science plays a part in our
Yeah,
environmental landscape.
yeah, showing how science is important in our environmental landscape, right? Yeah, yeah. Yeah, yes, I would say that those are kind of my intentions going with this course. And also, basically kind of breaking it down. So the course is called Science of Everyday Materials, right? And so we started first with just some common materials like cornstarch, ketchup, soap, and coffee. And then after that, once we learned the science of some common everyday materials, like how things are not just liquid or solid, they're kind of mixed, we also figured out how, in the recent chapter, that these concepts can help us understand collective properties, so like flocks of birds, right? If you have birds moving collectively together, they're more like one phase, like a liquid or solid. But then if they're dispersed and they're not moving collectively, they're like a gas. And another thing that we learned is that macroscopic physical properties like pressure and elasticity can basically emerge from how atoms interact with each other. So, um, so, so basically, epidemics are similar, right? Because, well, if you have individual molecules that are kind of bouncing around, Ken's, let me just mute you. Um, I'm hearing like an echo of myself, and that's a little bit harder. I'll just mute you, Reggie. I'll just mute you for now. And then when if you want to speak, you can just unmute yourself and speak. Right. So we kind of understood what pressure is, right? Remember how I talked about at a higher temperature, your molecules are moving faster and then they hit the edges of tires, right? But when the temperature becomes lower, then the speed of the molecules also decreases. And that leads to pressure reducing. So you just see pressure, your PSI, reading from your pressure gauge. But that doesn't tell you what's actually happening inside. But in fact, the individual molecules of gases are actually causing macroscopic properties like pressure or elasticity or viscosity. And epidemics are kind of in the same way, where it's not like the coronavirus suddenly is just spread around the earth and infecting everybody, right? It's how is the coronavirus transmitted?
People coming into direct contact with it, whether they're
Yeah.
breathing it in or touching it and then touching their face or something like that.
Yeah, people, it's through people, right? Ultimately. So it's people giving it to other people. So it's also something like very similar to molecules creating pressure, right? It's like individual people are ultimately causing the disease to be transmitted. So it's a microscope, the people leading to microscopic, where it's the world, right? Um, and one of the strategies to prevent it, it's very useful, is social distancing. And social distancing needs to be practiced by each individual person, right? You can't have like an antivirus solution that's just sprayed over the entire world. I mean, yeah, you could, but that'll be very ineffective. The most effective way is to deal with the microscopic, and then eventually you'll see the number of cases or the spread of the disease reducing. Does that make sense? The analogy that I was talking about?
Yeah.
Mhm. And in some sense, it's also similar to population growth. Where population, you might see a graph of population, right? And you'd see a very nice increase or decrease, a smooth curve. You might see a smooth curve. But ultimately, population is through individual deers reproducing, right? I should say two deers reproducing. Right? Any questions? Reggie, if you could mute yourself when you're not speaking, that'll be great. But feel free to unmute yourself once you want to speak. Okay. So I want to ask you this question: if deer have a lot of grass, and if let's say there are no predators, right? It's just deers on grass. How do you think the population of deer would change?
It would increase by a lot.
By a lot, right?
Mhm.
How would it go? Um, Let me see the chats. Rapid growth. Yep. Yeah. Um, so let me. share screen. It's just not being cooperative for today. Yeah, sorry. For some reason, the computer was not cooperating. Okay. All right. Okay. All right. Can you see the screen? The whiteboard?
Yeah.
Okay. All right. So let's say we have number of deer. This time, right? Let's say if you need two deer to reproduce, right? You need a male and a female. So let's say two deer give rise to two more deer, right? So I'm going to start off with two here. And then let's say 1 year later, I don't know how fast deers reproduce. I'm just going to say one because that's a nice. Next, 1, 2, 3, 4, 5 years, right? So let's say you have two deers, and then you have 4 deers after a year, right? How would that increase? Would that just keep going at a yeah, so how would that increase? Would that just keep going this way? Would that be is that how the number of deer might look like?
Are you asking like if there was a lot of grass and no predators?
Yeah, yeah.
No, it would probably go up way faster than that because you're only
Way
getting
faster.
two deers every year if it's a linear graph like that.
Would it be 2 deers every year?
No,
No, right? What would it be?
it would probably be maybe 10 times that. I don't even know.
Yeah, okay, so let's start. Let's say, well, if it was following the straight line, it would be 2, 4, 6, 8, 10, and then 5 years later, it would be 12 there, right? But that's not the case. So I'm just going to put 4 here. What's the case instead is, well, again, I'm saying like each deer can give one of each, right? So 2 deers can give 4, right? So it's actually it's 4 here. And then those 4 deers, how many would they produce?
Another 4,
Another 4. So it's actually 4 plus 4. That's what? What's that? 8,
8,
right? And then after 3 years, it's, what is it?
16.
16. So like way up here, right?
Mm-hmm.
So in fact, this would go something like,
It's like an exponential growth.
yep, yeah, exactly. So this would just be linear. So this would be exponential. And that's the difference between the linear and the exponential, right? That's the main difference. Where, you know, the linear is just you'd only have 12, but in 5 years you'd have 2, 4, 8, 16, 32, and then 64. So you'd have a huge difference. Yeah, it's like 2, 4, 8, 16, and then 32, and then at 5 years you would have 64, whereas you would have only predicted 12, right? So that's what exponential is. It's a huge rise. So if you instead think in factors of 10, before we were thinking factors of 2, right? If you think in factors of 10, you get 1, 10, 100, 1,000, just like that. And here you see what's the difference between the linear and the exponential. The linear is growing at a constant rate, whereas in the exponential, you're going by a constant factor. Any questions here? No questions? Okay. And the other thing is, if you looked at something like the virus, right, what you would see is, let's say these are weeks, right, or months. Maybe these are more like a month scale, where you take a month to go from 1 to 10 cases, right? And then you take a month to go from 10 to 100. You take a month to go from 100 to 1,000. And until here, nobody's really noticing. I don't know if you remember, but when we were stopping class, I was telling you about it, and then I was saying, well, it's 400, right? And that was still scary. But then after a point, it go from 1,000 to 10,000, and you're just like, oh wait, it's 10,000. That just grew on me. And you might think that, well, it's suddenly it's growing, it's going faster than it used to. No, it's not. It's an exponential. It's always been an exponential. Um, for the most part, there's some, at really small numbers here. If you just have 4 or 5 cases in the entire United States, then there's a lot of fluctuation. Problem is here when you go from 1,000 to 10,000, it becomes very predictable, but you don't want it to be, right? You don't want it to be so rapidly increasing. And then once it's like this, you really can't just isolate 10,000 people all of a sudden, right? It becomes much harder. Whereas if you just had a linear growth, you'd see the same rate. You'd see 1 to 2, 2 to 3, or even if you had linear growth 1 to 10, then maybe after 10 you have 20, 30, 40, right? You'll see that. So this is the equation for a linear curve. Here is what you see is that if population is linear, then it would change at a constant rate. So the slope of the graph would be a constant. Right? Let's say the slope is r. So let's go ahead and draw that out. Okay. So let's say I have a graph of p versus time, right? And this is dp, dt. So what you have is, and let's say it's p0 at time 0. At this point here. So what's the equation of this line? Well, if the slope, that's delta p over delta t is r, then your p is r times t plus a p naught. So let's say, well, if this is your population again, right? Let's say you initially had, let's just say it's 1. Maybe you're talking about bacteria now. Bacteria can just divide, single bacteria can divide. And then so if your population is 1, initially you have 1. And you grow at basically 1 bacterium per hour. Bacterium per hour. Then your population, if this were true, I'm going to say it's later that it's not true, but if it were true, then your population would be your initial population 1, initial number of bacteria plus 8, that's 1, times, let's say, 5 hours. So 6 bacteria. Right. So is this true? Would this be true? Let's figure out how to do this. Right. Any questions?
So is P0 in the equation that you just did?
Uh-huh.
Is P0 1 in that case?
Yes. So I just took an example where, let's say I had bacteria and I had one bacterium to start off with.
Mm-hmm.
Yeah.
Okay. And okay, I see.
Mm-hmm. So we know that for just a regular linear curve, what you have is basically your population, your rate is fixed, right? That's what we know for a linear curve, where basically your slope is a constant, and that you can use the equation. But for an exponential, we just established that it goes much faster, right? Right. So what do you think the equation might be? And you know how an exponential looks. It looks like this. Would this be changing with the slope? Does it look like it's changing?
Yeah, it would have a different thing in there. Probably would, I guess, throw in an exponent somewhere, probably.
What exponent? Can you clarify?
Um, so I guess it would still be the delta P over T,
Mm-hmm.
or delta P over delta T.
Yeah.
Um, and then um R squared? I don't know.
Oh,
I'm just
that's,
guessing.
I guess, r squared, right? So here's the problem with that. If you say, well, a linear would be r, and then this would be r squared, then well, r is just a constant. So if it could be r squared or r cubed, but you know, it might be like, I guess the best thing that you do with a linear, you could have something like this. Oh, sorry. Yeah, something like this, right? But that doesn't match up because ultimately this one's going to win, like, you know, a million years down the line. So this might be r squared, and well, I'm just going to use some different colors. Maybe this is r squared, right? So it's not just that. It's not just, you can't just increase the rate. Right? Does that make sense?
Yeah.
So what do you do? Well, it turns out that in the most simple case, you can think about it as rate is proportional to the current value. So your rate of increase is proportional to your current value. So let's say for the simplistic case that your rate is equal to your current value, right? Which is why I put equal to. In general, it wouldn't be exactly equal. It could be a factor here. It could be like, I don't know, k times p, but let's say it's just that. So let's say your say p naught is equal to 1, right? Then what would your delta? So in general, your p1 would be p naught plus your delta p, right? I mean, this might be a little bit too much math. So
The
instead, I'm just going to write your delta p or delta t would just be p naught, that's 1. So your new p1, what is that?
P naught plus
It would be basically your p naught plus your change in
yeah.
p. So it would just be, so let me see, your delta t is 1r, p1 after 1r is just, it's just p naught is 1 plus delta p is all, after 1r is also 1. So that's just 2, right? Does that make sense? I need to figure out how to use this. I'm kind of stuck in this corner. Is there anything to move? No, there's something. All right. So your population 1 after 1 hour is 2. And in the same way, after 2 hours, your delta p or delta t is what is your p1, that is your p1 is 2. So now your new population p2, the p1 plus delta p, that's, and delta p is 2. So that's just 4, right? So basically this is kind of cumulative, right? Your slope your slope at any given point in time is basically what value you are at that time. So you just increase by that. So this is basically a simple case, just doubling every hour. Right? Does any questions here?
So the
Please let me.
expon
Yeah.
so the exponential growth formula or slope formula for this is um P2 plus delta P, or I'm confused.
So in general, if you keep doing that, what you find is that the exponential formula goes as this. This is the exponential formula. I was just going to come to that. So if you have delta P or delta T as P, then this is your exponential formula. Um, in general, what you have is there's another rate factor that goes here, and that just goes in the numerator. Does that make sense? So remember how we did in the coffee, the time it takes for all the coffee to get out of your body, and that was an exponential decay. This is kind of the opposite. It's an exponential increase, right? So this is the formula for the exponential growth. Any questions? I need you guys to understand this because after this we're going to talk about something that's a little bit more complicated with what happens if there's a finite amount of grass, things like that, finite amount of food, right? But basically, just to summarize this part, yeah, I just saw a question in the chat. I'll get to that. But to summarize this part, what the idea is that in linear growth, the rate at which you're growing is a constant. But in exponential, the rate at which you're growing is proportional to the actual value you are at a certain time, and that just accumulates. And that you get this formula for exponential growth, the e to the power of um, time.
Is R like the rate or something? Like,
Yeah, in this case, it's called a rate constant. It's not the same as a slope, but yes, it's a rate.
okay.
What this will tell you, this R, it kind of tells you like depending on the change of R, it'll tell you like, for example, the coronavirus doubles every few days or something, right? So if it were a week or a month, then that would change this value of R here. That's what will change. But P0 is the initial value. So if they're initially like 100 coronavirus patients just bombard the US, right? Or is it just one? How did it start off? Same thing with
And
deer. Did 100 deer enter grassland, or was it just 2 deer, right? Yeah. So there's
and
just two factors that determines an exponential growth.
what's E?
E is the exponent. It's
Okay.
the e to the power of. So essentially, if you knew calculus, what you would realize is that this idea that I talked about, where your rate of change is proportional to your population, when you solve this equation, you get this. But that's not important for us because we don't need to solve it. We just need to. You guys don't need to solve it. You just need to know that it's going to be increasing as e to the power. And where does this come from? Well, this comes from the idea that the rate of change is proportional to your population, and it's not a constant. Okay, you want to do one more example. Even an example of an expression. Okay. Let me think of a good example. Okay. So let's say you had, let's just take this bacteria example. Let's say you, I'm going to type this. So you had bacteria initially. So let's say you had a tree, and the tree grows exponentially. Um, Initially, it is 1 millimeter. And so what's, so the question is, what's the height at 1 year, 2 years, 5 years, and then 10 years? So what is the equation that you would use? You would use h is equal to e to the t. So what's the height? Can somebody calculate that and tell me, and then
Is it just one?
what's the height after 1 year? So, no, it's not.
Oh, well, I don't know. I was saying because I thought if T is in years and
Oh,
you're
it's
saying
0,
like
it's 1. At 0 year, so initially it's 1
right,
millimeter, right?
right.
But at 1 year, what is after a year? So that's the question I'm asking you. Can anybody tell me how to do this? Anybody have any questions?
If it's starting at 1, right? So then what's E?
Oh,
Just
you would plug that into your calculators.
oh,
Right.
okay.
Yeah. That's the same E, the exponential. The same thing that you did when you were looking at the radioactive decay of coffee. Not radioactive, just the decay of coffee, like based on how the half-life and um, how long it take to get out of your system and things like that, right? The same exponential. That was a decay, but this is a growth. All right, is it 2.7? Yes, I think that sounds about right. So it's 2.7. What's the units? Millimeter. Yes, that's correct. Oh, what's the height? 7 point something. Somebody said 7.4. 7.4 millimeters. So still not big at all. It's not even centimeter at that point, right? What about after 5 years? One hundred 48 millimeters. What about 10 years? So 100 millimeters, right? After 5 years, it's like a cup tall or something. Right? It's like 1, 2, 3, yeah, like 10 centimeters. After 10 years, 22,000 millimeters. And how much in meters? How much is that in meters? No, it's not 200. So a millimeter is 1,022. Yeah. So 1,000 millimeters is a meter. So it's 22,000. 1,000 divided by 1,000. That's 22 meters. That's reasonable, right? After 10 years, it's as tall as a building. But what what you might not, the interesting thing is you see how after 1 and 2 years, you might not even notice the tree, right? You might have just stepped on it and might have died. But the interesting thing is until 5 years, it's just like a cup. But then between 5 and 10, it's just a huge increase. Right? And that's not because suddenly something has changed. It's just because that's how it works with the exponential. Right? Any questions here? All right, let me give you another example, a more relevant example. Let's say, and this is not to scare you guys, but this is just to illustrate, right? Let's say coronavirus increases. Um, let's say mm, let's say this goes as again t, the number of cases. Here the t, where here t is like 1 week. Start off at 1 person. So what's the number of cases after 2 weeks? And we're just going to say this is the US. How many cases after 2 weeks? How did he get 7? Can you explain how he got 7? Oh yes, 7. Yes, you're right. It's 7. So there's 7 cases after 2 weeks. It's 7 point something, but you can imagine that, well, uh, let's say these 7, I quarantined them. I didn't let them cruise ship, right? Or I kept them in a particular room. I mean, I don't think the cruise ship example is good because that didn't work. But uh, let's say I quarantine them or something. But the problem is we don't know, we can't identify the 7. And that 7, you can imagine that there's so many things that happen. Maybe they didn't. Um, it's fluctuating. It's not exactly exponential. Maybe it's like 6 or 5, and that will cause some differences. Now let's say number of cases after 3 weeks. No, let's you know what? Let's just do it. I'm not going to do after 5 weeks. So let's see now what happens. Tell me what's after 5, after 10, after 15. Also after 20. Okay, so somebody said 148, yes, and then 5 weeks, and then after that, what? 10 weeks. Yeah, it's 22,026. Now we're starting to see. It may be, in somewhere between 7 and when it was 140, we were like, oh, it's just 100. That's now it's 22,000, and then after 15, it's 3 million. How much is that? 3 million after 15 weeks. And how much after 20 weeks? 485 million, right? At a certain point, you're like, you know what the population of the US is? It's too much, right? So something's changing at that point. So exponential is actually a good model for the first initial rise. So right now, I think exponential is still a good model, but hopefully things change, and things definitely change. One thing that'll change for sure is, yeah, but even if every person was affected, which is definitely not going to happen. Yeah. So something changes, and that's what we will talk about a little bit in the next class. Where, yeah, this is not going to happen. This is not going to happen. It's going to slow down. You might have heard people saying we're still on the rise. We don't know whether we hit the peak. So what happens when you hit the peak, right? That's what we'll talk about next class. Are there any questions before we sign off? And again, I don't want to leave this at a bleak note, but it's looking like we might hit the peak in a couple of weeks or something. I know. I look at the charts every day and I try to match it to see what's happening, and then so hopefully very soon, we're still on that rise, but then we'll kind of hit the peak, and then so tomorrow we'll talk about hitting the peak in terms of population, and then we'll also go to epidemics and we'll talk about you hit the peak and then you come down because because you don't just have infections growing, you have other stuff, right? You have people recovering, you have vaccines, you have science. Yeah. All right. So the lab, yes, we have a lab at 10 o'clock. So I'll see you guys in 45 minutes. And you just come in here and we'll transfer off Teams and we'll do an online simulation there. Okay. All right. Any other questions before I see you guys at 10?
You said we just come back here, or do we go on Microsoft Teams?
You come back here and then we will talk a little bit. I'll give you an introduction to the lab and then we move to Teams.
Okay.
Okay. All right. See you guys.